Assalamualaikum warahmatullahi wabarakatuh and very good morning to Dr. Fatima. Today we are excited to present our project for computer organization and architecture, which is the to start, let me explain the purpose of this circuit. The logic unit is a key part of the CPU's arithmetic logic unit, ALU. Unlike an adder that does math, this unit performs logical operation. It compares bits using gates like AND, OR, XOR, and NOT to help the computer make decision. Now, I will pass to Shazwani to explain the theory.
Assalamualaikum, my name is Shazwani Atira binti Muhammad Faris. So, moving on to the logic verification. To ensure our design is accurate, we test the Boolean function using a specific set of input as shown in this table. So, we use input A as 1010 and input B as 1100 for all operations. So, first, for an operation, when the control setting is 00, the circuit performs a bitwise AND. Comparing 1010 and 1100 give us 1000. So, as you can see, the result is a pass. Second, for OR, the logic combine the bits, resulting in 1110. Third, for XOR or exclusive OR, the detects differences between the bits. The result is 0110. Finally, for NOT, this operation only affects input A. It invert 1010 to become 0101. So, this table confirms that our logic gates are functioning exactly as intended according to Boolean law.
Assalamualaikum, I am Shabil. Now I will explain about simulation design that include input, gates, and control signal. Now, let's look how we build in the logism. Our design have three main components. First is the input. We have 2-bit input that label as A and B. Next, the gate. We use a basic logic gate such as AND, OR, XOR, and NOT that wire in parallel. Lastly, the control signal. This is the most critical part. We use a 2-bit selector connected to the multiplexer to control the operations. That's all. I will pass to my teammate.
Thank you, Shabil. So here is the screenshot of our final circuit. It might be complex with all the wires, but it's actually modular. We built a 1-bit slice first and then replicated it 4 times to handle 4-bit data. This ensures the design is organized and easy to troubleshoot. Now, let's dive deeper into how this circuit actually functions. You might think the computer does one thing at a time, but our design works differently. There are 3 key mechanisms here. First is parallel execution. When we feed data into input A and input B, the circuit does not wait. It performs all 4 operations, which is AND, OR, XOR, and NOT. Imagine 4 workers doing 4 different jobs at the exact time using the same materials. Second is the selection logic. This is where the multiplexer or MUX comes in. Even though all 4 answers are ready, the MUX acts like a gatekeeper. It blocks 3 of the results and only opens the door for 1 result to pass through. Finally, precisions. The MUX decides which door to open based on the selector value we set. This ensures the CPU receives the exact result it requested for a specific instruction without any confusion.
Now, where do we actually use the circuit? It is not just a theory, it is a critical component in the real world. Firstly, ALU integration. This specific circuit is the hardware foundation inside the arithmetic logic unit of modern CPUs, such as ARM or x86 processor found in your phones and laptops. Secondly, bit masking. We use the AND gate logic for bit masking. This allows software to filter out or clear specific bits in memory, which is essential for network configuration. Thirdly, error detection. This XOR gate is crucial here. It is used to generate parity bits to check if data has been corrupted during transmission. Lastly, logical comparison. The ALU uses these gates to physically execute programming statements like if and OR that we write in our code. So, without this simple logic unit, a computer cannot make decisions or process complex data.
Now we will demonstrate the simulation live in logism.
I will set A as 1100 and B as 1010. Next, I will pass to my teammate to explain more about this.
Now we set the selector for the end operation as 00. As you can see that the output is 100. This is correct because for the end operation is 1 and 0 is 0. Next, we will change the selector into 01 for OR. So the output will display 1110. After that, we change the selector to 10 for the XOR operation. As you can see, the result is 0110. Finally, let us note A by changing the selector to 11. The output will become the inverse of A.
As you can see, the simulation ran perfectly without error.
Before we conclude our presentation, I would like to share the challenges we faced while building the circuit. It wasn't always smooth sailing. First, wiring complexity. As you can see in our earlier screenshots, organizing the 4-bit bus for each individual slice was quite difficult. The wires become very messy, so we had to use tunnels in Logisim. This helped us hide the wires and maintain a clean layout for the final submission. Second component is selection. We also face issues with the multiplexer. Ensuring the 4-1 multiplexer was correctly mapped to our 2-bit control signal was tricky. We had to test it multiple times to ensure the selector point. To wrap up, our group has successfully built a fully functional 4-bit logic unit that performs all operations accurately. This project shows us how simple unit gates combine to form the decision-making core of a computer. We now had a better understanding of how these components work together as the brain of the hardware. That's all from us. Thank you for listening.